Trigonometric identity is a statement that is true for all values of the variable and must include trig expressions. So a trigonometric identity means that no matter what I fill in for x, left side would equal right side. Okay? So a counterexample, a case where something is not true takes only one to disprove it. So if I have a counterexample, if I find one x that doesn't work, it immediately kicks it out and it doesn't work for all of them. You can't just find it for some and then say it works for everything. If you find one that doesn't work, it immediately doesn't. So here, we're going to verify, and this comes up in the curriculum. We need to verify, okay? We have to verify that sine x tan x equals cos x. Now, when you verify, paying attention, you move nothing from one side to the other, ever, across the equal sign. And your first step for verifying is filling in the degree symbol. There is nothing more painful than someone on the diploma, when you're marking something and they ask you to verify something, and they go and sub in stuff for tan, which you won't do right now because you haven't learned this yet, but once you start learning it, they sub stuff in for tan, and then they do some math. You can't do that. For verify, you're verifying that if I put 45 degrees into here, left side will equal right side. That's what verify means. And you put 45 degrees in, you do some math, left side equals right side. That's a verify. Okay? So you're verifying that it works for this equation, not a variation of that equation. So you can't change it. So your first step for verifying always is going to be to substitute in for x. So we are going to do sine 45 degrees, tan 45 degrees.
No, that's wrong.
I have cos 45 degrees.
They don't equal.
Well, it says here to verify that it is not an identity, so I'm hopeful that they don't equal. Okay. So we're going to plug in 45s. Now, you cannot just type this into your calculator. That is not a verification. Yeah, you did it. It's not a verification. You need to actually show some algebra. So you might as well just leave your calculator sit. You don't want them. I know you might want them, but you can't have them. Sine 45. Go to your unit circle. What is sine 45? Root 2 over 2. So watch. I know that sine 45 is root 2 over 2. So I replace the whole thing with root 2 over 2. We agree? Because sine 45 is root 2 over 2. Yes? Okay. Tan 45 is 1. All the 45s for tan are either 1 or negative 1, depending on if they're, you can use casserole or you can use, hey, it's root 2 over 2 divided by root 2 over 2, right? Which is a 1. So we get times 1 equals, we treat our equal sign like it's a zapper. If you cross over it, you'd be zapped and dead. It'd be real bad. So don't do that. Cos 45. It's like an electric fence, this little two little lines. Don't cross over. Cos 45. There'd be one of those boys trying to touch it. Is it going to hurt me? That's what you would do. Yeah, exactly. Don't. Cos 45 is root 2 over 2. Wait a second. What happens here? Hey, equal.
No.
Root 2. Yes. Root 2 over... But that's because you put it in your calculator. It's probably in degree mode. No. Root 2 over 2 equals root 2 over 2. So... left side equals right side. It needs to be in degree mode. You put degrees in.
You get the question wrong.
Shoot. Yeah.
You get the question wrong if you don't put right side equals left side.
Left side is right. Yep. You will lose marks. You absolutely will.
That's what's the case.
Yep. You will. And then why did you double? I can't even take. I can't. Yes, you will. They'll take off 0.5 for sure on a written response. And you have to in university as well. Once you get past like first year university, everything's like most of your maths just proofs. I have to prove on like by 7 boards but there are infinitely many prime numbers.
That sounds so boring. But it is correct.
Huh, shocking. Okay, yeah.
Does it matter how you separate them? Like if you just use a line or just a sign? 'Cause
It-
I'm sorry.
If you use a line, you have to label it as left side and right
Yeah,
side.
yeah,
Totally fine.
Okay.
Do you have to like spell it out? Because like sometimes like if it's like horizontal
The only thing you can short form in all of mathematics is LS and RS because it is an actual, in a math curriculum statement definition. So enjoy your short form. It's the only thing you get. Okay? So how else could you do it? You could go left side. And you could go right side. And now the line in between is your zapping line. Either way, don't cross it. It'll get you. Okay? So let's plug in left side. We have to plug in the 30. So we get sine 30 degrees, tan of 30 degrees. And I'm going to explain the difference of these two and what you need to have in order to get full marks. Cos of 30.
These ones
Talking to a movie theater and tell people how it ends. So he does. Yeah, he would. So if you look at the left one over here, the left one, I didn't write left side, right side, right? So that's my little bit of short form. I don't have to write the left side, right side. I put equal signs down the middle. Paying attention, because if you pick one or the other, you need to know what you exactly need to do to get full marks. If you do this one, you have to have an equal sign in the middle of every single one, and your left side has to follow all the way down, and your right side has to follow all the way down. So you always have to have a left equal a right, a left equal a right, a left equal a right, a left equal a right. Okay? If you choose this one, you're going to have to write left side and right side. You have to do your table, but you can do whatever you want over here, do whatever you want over here until they match. They can be lopsided. And you have to go, then you have to write left side equals right side again. Different ways, yeah?
Do you have to like fully write left side, right side, or can you just do like the LSRS?
I would say you can do LSRS since it's LSRS is acceptable there.
Okay.
Yeah.
Yes.
So if you use the equal sign, you have to have a left and right side on the equal sign every single time. You have to carry it down. If you do a table, you can run. You have to write left side, right side, LSRS, whatever. Do a table. Run the left side down however far it takes till it matches the right side however far it takes. And then at the end, at the bottom, go LS equals RS. Optional, but both have to be done correctly. So I've seen people do this one with the equal sign, and they like don't write anything on the right side for a while and then bring it back. You won't get marks because it's not a proof. Left side is equal right side, left side equal right side. So if you do the equal sign, you have to make left side and right side always have something. If you do this one, you can run down both sides. Okay? Make sense? Okay. So sine of 30 is what on the unit circle?
1/2.
1/2. Tan of 30, what's that?
Root 3 over 2. No, root 3 over 2 divided. Yeah, 1/2 divided by root 3 over 2.
It's going to be a half divided by root 3 over 2, which is a half times 2 over root 3, which is actually 1 over root 3, which we know rationalizes to root 3 over 3. All tan 30s will get you root 3 over 3s or negative root 3 over 3s, right, depending on cast. All tan 60s will get you just root 3s or negative root 3s, right? So tan 60s are actually nicer than tan 30s. Tan 30s are the fractional ones. So I'm going to get tan of 30 is root 3 over 3. And then I can keep going down the left side all I want, right? I can go, when you do fractions, you go across top, across the bottom. So I'm going to get root 3 over
6.
6. And this cos of 30 equals what? Root 3 over 2. Do these match?
No.
No. So you would say at the end, left side does not equal right side. And you just prove this isn't an identity. You can verify it for one answer, that's great, but the moment I got a counterexample, it's out. Okay? Note, counterexamples can disprove a statement, but examples cannot prove a statement. So if you get one example that works, you can say, oh, it works for that example. And you can do another example and it works, oh, it works for that example. And you can do 100 examples that work, and you can say it works for all 100 examples. But you can't say that's a proof. I have no idea what just happened. You can't say that's a proof if you fill a number in. Okay? So, non-permissible values. Let's look at this. Non-permissible values happen when you have a denominator with a variable in it. Correct? We talked about it in rationals last year. The moment you have a variable in your denominator, you have non-permissible values. You have values that don't exist. And you have values that don't exist because your denominator would be 0. Correct? So, non-permissible values. The denominator of a fraction can never equal 0. So, for every trigonometric ratio or variable that appears in the denominator of a fraction, it will result in non-permissible values. So, if you have cosecant anywhere, you're going to get a non-permissible value because cosecant is 1 over sine. Okay? So wherever sine theta equals 0, we have problems. Correct? For cosecant? Sine is y or x? Y. Where is y equal to 0? Yeah, x-axis. So where is that? 0, 180, 360, negative 180, negative 360, all of those, correct? So the way to state non-permissible values is you actually have to state a general solution because it has to encompass all of those. So, what can't theta equal? Theta cannot equal 0. That's my first principal angle, right? Let's do it in degrees. 0 degrees, and then we'll do radians after. Plus, when does the next one happen?
180.
And then, he's trying to be really fast. And then 180, and then 180, and then 180. So what do we write that as?
180 degrees N.
180 degrees N. What else do we need? N. Right. Do I need to write the 0? No. So technically, whenever I have sine in the denominator, I'm going to get theta can't equal 180 degrees N. NEI, or in radians, that would be pi n, NEI. So whenever you get a sine denominator, you're going to have those non-permissible values every single time. Whenever you get cosecant, you're going to have those non-permissible values because you're going to have a division of sine. Okay? What about secant? That's going to be cos. Cos can't equal 0. Where the heck does cos theta equal 0?
The y-axis.
The y-axis. Where's the first one then?
90.
And then?
270.
So it's going to be 90 then, 180 then, 180 then, 180, or 90 minus 180 would be going actually this way. I'm going the wrong way. I'm going my way for myself, the opposite of you. So our first one would be theta equals 90 degrees plus 180 degrees N, NEI, or in radians, that's what I have. And then in radians, it would be theta cannot equal, what's 90 in radians?
Pi halves.
Pi halves plus pi N, NEI. What about tan?
No idea.
1 over x.
Tan is actually both y and both x. Tan is actually both sine and both cos. So I have sine in the denominator and cos in the denominator, don't I? So think about it. Tan. So tan can't equal 0. Which means sine theta over cos theta can't equal 0. Remember that at 90s and 270s, tan actually doesn't exist. So not only does it not equal 0, it don't exist, correct? And then at pi and 2 pi and 0, it's equal to 0, which is a problem. So actually, when you have tan in the denominator, you got issues at every single axis, right? Do we agree? So you have issues here because those are asymptotes. You have issues here because they're zeros. So it's going to be every single one. It's also where sine can't be. Sine can't be at every x-axis. Cos can't be at every y-axis, right? So it's every single thing. So where would the first one happen at then? 0, and then every 90 after that, correct? So I could go theta can't equal 0, which I'm not going to do in a second. 0 plus 90 degrees n, NEI, but we never write the 0, so we're going to go 90 degrees n, NEI, or in radian measure, can't equal pi halves n, NEI. Okay? Does that make sense? Every single 90? And then what if we have tan theta? Tan theta is the same as sine over cos, is it not?
Yeah.
Is tan the same as sine over cos? So what's my problem when I see a tan? What's in the denominator when I say a tan? A cos. Cos is in my denominator, correct? So whenever I have a tan, I have to state NPVs for cos theta can't equal 0. And then somebody say, well, why over there did I have to state it for both? Where's tan in that one? The tan is in the denominator, so I could literally rewrite this, instead of writing it as cotan equals 1 over tan, I could write it as cotan equals sine theta over cos theta. So both of these are actually in the denominator, aren't they? You see that? That's why sine and cos had to be counted for that one. Whereas this one's just a plain old tan. So the only thing that's in my denominator is cos. So this follows the same restrictions as secant, technically, which would be wherever cos is 0, I can't be. So 90 degrees n, I'm sorry, 90 degrees plus 180 degrees n NEI. Or pi over 2 plus pi n NEI. For cotan, what's in my denominator? The sine, right? So what can't equal 0? Just the sine, right? And where is that happening at? Sine happens to be at 0, 180, 360, right? So it's 0 plus 180n NEI, but we don't write the 0. So it's just going to be theta can't equal 180 degrees n NEI. Or theta can't equal pi n NEI. Now what if instead of 1 over tan, I gave you 1 over cotan, just to try? What if I gave you this? What is cotan? What's cotan also? Cos over sine, isn't it? So this would be the same as 1 over cos theta sine theta. So what NPVs would it have? The exact same as sine and cos for the tan one, right? So it would be every 90. So if this was a question, I would have theta can't equal pi over 2n NEI, or theta can't equal 90 degrees n NEI. Right? Let me flip over. Okay. We're going to start looking at the formulas on your formula sheet. There's so many on the right-hand side. That's where we're going to be best friends with that formula sheet. So here it says From a squared plus b squared equals c squared, we can get sine squared plus cos squared equals 1. Now, why can we do that? Because the formula is x squared plus y squared equals 1, or in this case, y squared plus x squared equals 1, because coses are x's, sines are y's, right? It's just the same thing. If you look on the right-hand side of your formula sheet, I have one up here. We have, it's called the Pythagorean theorem identity, because we use the Pythagorean theorem to get it. Sine squared plus cos squared equals 1. It's on the formula sheet. It's also up there, right? Same thing. So on the right-hand side of your formula sheet, you will see it. Now, here it says, divide every term found in sine squared theta plus cos squared theta equals 1 by cos squared theta. Let's see what happens. So if we divide all of this Pythagorean theorem identity by cos squared, what do we get? So sine squared theta divided by cos squared theta. Yep, we're going to get there. Cos squared theta over cos squared theta equals 1 over cos squared theta. So we just divided them all by cos squared, right? What is this? Sine squared over cos squared is? Tan squared theta. Plus, what's cos squared divided by cos squared? A 1. And then what's 1 over cos squared? Nope, look at your formula sheet. You have a 1 over cos on there. It's secant squared. Where do we find this formula that we just made? Look on your formula sheet. It's right below the Pythagorean theorem 1. Sine squared plus cos squared x equals 1. We know where we get that one from. It's just our unit circle, correct? The second one, 1 plus tan squared theta equals secant squared theta, comes from just taking that same one and dividing it by cos. All of them. Okay? How we guess it's going to happen on the third one. So the third one, we're going to divide them all by sine squared. So we're going to do sine squared theta divided by sine squared theta plus cos squared theta divided by cos squared theta equals 1 over cos squared theta. I'm just dividing them all by cos, right? And by cos I mean sine. Oh my goodness. You're welcome. Sine squared theta. A little bit of the last question, and with this question, it went a little wry. We're on period 4. My brain sometimes halts. It's real. Sine squared divided by sine squared is what? 1. I'm going to change my color. This is 1. What's cos squared divided by sine squared? Cotangent squared. And what's 1 divided by sine squared? Cosecant squared. Remarkable. It's the third equation. See how that happened? Just line them all right up there, okay? Look at this. Boom, boom, boom. Life can't get much better, really. You think like pie or something, but you're wrong. So, yeah. And I mean like food pie, not pie. All right. Yes. Okay. What's cool about formulas? You can rearrange them. Is it 3 o'clock yet? No, darn, it's still here.
I got like 6 minutes. I'll count down.
So we have sine squared plus cos squared equals 1. Okay? So that's a formula. Formulas can be moved around. If you don't believe me, you've never been in math or chem or physics, because they move like crazy in those subjects. All right? What else could I do? So instead of going sine squared theta plus cos squared theta equals 1, what other way could I rewrite this equation? What can I do with this sine squared? Yeah. Yeah.
You could subtract it, and then you could just do cos squared is equal to 1 minus sine squared.
Yes, is equal to 1 minus sine squared. You're right. Anything else we could do?
Yeah.
Yeah.
Subtract 1 to make it negative 1 plus sine squared theta plus cos squared theta equals 0.
Move them all to one side?
Yeah.
Yeah, sure. Sine squared theta plus cos squared theta minus 1 equals 0. What else could we do?
Yeah, let's say minus cos and sine on the other side.
Yeah, minus cos. So we get the same thing up here, but instead of it being minus sine, it would be
Yeah.
minus cos. So sine squared theta equals 1 minus cos squared theta. You know what else they can get?
Could you do cos squared theta plus sine squared theta?
So ready there. Yeah, rearrange it. Yeah, I agree. Yeah. What else could you do? Could we move the 1 over and then move one of them over? We're not square rooting anything. That's just crazy. I was just going to say move the cos squared over and move the 1 over. Because you can sometimes get negative cos squared, can't you? So you could move the cos squared and the 1 over, so you could go sine squared theta minus 1 by moving the 1 over equals negative cos squared theta. Right? If I need a negative cos squared. I could do the same for sine. I could move the sine squared over and then the 1 over and get cos squared theta minus 1 equals negative sine squared theta, right? So this formula can be moved around quite a bit, can't it? Most often they're just replacing the sine squared of the cos squareds. So most often it's going to be like cos squared gets replaced with 1 minus sine. Sine squared gets replaced with 1 minus cos. Most often that's what we do. But there are different variations. Okay, what about number 2, the tan one? Tan squared theta plus 1 equals secant. What could I do? Yeah.
Tan squared equals secant squared minus 1.
Guten Tag. Oh, it's a good day, isn't it?
No, it's like. It's like.
Isn't it a good day?
No, Avita saying is goodbye. I'm going to Germany in December. Wrong.
Next one we could do. We could move the tan squared over, so we could go 1 equals secant squared theta minus tan squared theta. We could, if we had a negative secant, we could force a negative secant. Shh. So we can move the secant over and everything else to the other side, couldn't we? So we could go like negative secant squared theta by subtracting it over. Then we'd have to subtract all that over. So negative tan squared theta minus 1. So you could do variations. But like I said, majority of the time the variation is going to be, I need to replace a tan squared. So I'm going to replace it with secant squared theta minus 1 or something like that. Or I need to replace the secant squared theta minus 1. And I can replace it with a tan squared. Okay? And then 1 plus cotan equals cosecant. What could I do? I could move the 1 over. I could go cotan squared theta equals cosecant squared theta minus 1. What else could I do? Could I swap the cosecant with the cotan? Yeah. I could make it be 1 minus cosecant squared theta equals negative cotan squared theta. Basically, the send home here is these formulas are given to you, but every variation isn't given to you. But you need to know what you can move them around to get. I can get a secant squared by itself, correct? I can get a tan squared by itself. I can get a cotan. I can get any of them by myself. Now the thing is you're given a formula sheet that has a ton of formulas on it. There are a ton, and you don't have to memorize them because they're on the formula sheet, correct? But the people who do not know what formulas are on this formula sheet do terrible in this unit. Because you have to like see, oh, 2 sine squared cos, or 2 sine x cos x. Oh, right, I know there's a formula for that. You need to know that, hey, I know there's a formula for that. Then go to the formula sheet and find it, that's fine. But you need to know that there is a formula for certain things, right? You have to be able to spot it. So the people who know the formula sheet actually do way better. They know it. So they know what's on there. They're not searching for 20 years trying to find something. Okay, We're going to verify that each identity above is true. So to verify it, we can go left side. Right side. You can go LSRS. I'm being lazy. I mean, I'm not being unlazy. I don't know. Opposite of lazy. So I have sine squared plus cos squared equals 1, correct? Now that's my first step for verifying. Fill in the...
Thanks.
Yes. So it's technically a theta, but that's fine.
Yeah.
So we're going to get sine of pi over 3. Wait a second, there's a squared sitting in here. Remember how I gave you a quiz when there was a squared sitting in there? What did you do? You took the answer. Yeah, and you squared it because you square the whole thing. Yep. And then plus cos squared theta and then 1. Isn't that a beautiful right side? I don't think it's going to get any better. It's just like there. Okay. So what's pi over 3? Sine pi over 3. Yep.
0.182.
Some people's children, seriously.
Radian.
Put down your calculator. Are you in degree mode? That's even better because you're doing it. No, don't use your calculator. Put it down. Cos of pi over 3. So we go to pi over 3. And what's cos? 1 over 2. What happens when you square a square root? It ceases to exist, sure. So it just goes away. So we get a 3, and then 2 squared is 4. Plus 1 squared is 1 over 2 squared is. So I get 4 over 4, which equals 1. Look at that. LS equals RS. Don't forget it. Très important. Okay?
The next one.
We'll do one more. So we're going to do tan squared theta plus 1 equals secant squared theta. Don't put the wrong side. Tan squared theta is pi over 3. 1 plus tan squared. Oops. Secant squared theta. 1 plus, what is tan at pi over 3? That's at a 60. What's at a 60? Root 3. When you get 60s, tans at 60s, you will throw a party in your head because it's root 3. It's like the greatest thing ever. When you get tans at 30s, you get fractions. Not as greatest thing ever. Okay? So it's going to be root 3 squared. Now what's secant? You can work down one side, work down one side, work one side and the other at the same time, doesn't matter. What's, yeah, because cos at pi over 3 is a half. So secant and a half is x over r. So secant is r over x, which would be 2. And then here we get 1 plus 3. Oh, squared. 1 plus 3, which is 4. 2 squared is 4. So what can I say? Left side equals right side. So is this a proof that this works for every single thing in the world? Everything's great. I've just proven it. I put in one number. That means it works for everything. Does that make realistic ideas in your head? No. If I say to you, hey, I proved for one thing it works for everything, you'd be like, no, that's not a proof at all. Right? That's a verification. You're verifying that it works for pi over 3, and that's all we've done. Okay? Okay. You're going to see some weird things going on in your notes, because for some reason,
Oh, what about the cotangent one?
That we're only doing 2. You're going to see in your notes, for this one it's fine, but you see in this one it gives you like an extra sine, an extra cotangent, and an extra cos without x's. Those just get crossed off. So it's supposed to be sine x plus cotan x plus cos x, or times cos x. So just cross off the sine, cross off the cotan, cross off the cos. Or if I were you, I'd just rewrite it underneath. That's what I would do. So the top one's fine, and then after that it just causes itself issues. I don't know. So we're going to simplify the expression in example 1. We have cosecant x equals cos x cotan x. So when they're singles, it's something to note. When you have singles, like single cos is not cos squared, you know what I mean? 3 ones. Your only options for the most part, except for like 2 cos x down here, is just these ones up here. I can replace a tan with the sine over cos. I can replace cosecant with the 1 over sine. You see? Just these single ones up here. That's all I kind of have options for. Okay? And what you want to do always in simplifying for the most part is switch them to sines and coses. Yeah.
Is this supposed to be minus or equal? Is this like equal to progressive?
This is a minus. Did I say equals? There's a chance. We could go back reel the film. I'm sure I probably did say equals, but I meant minus. So cosecant is what? 1 over, sine x off of our formula sheet. It's right there. So this equals, this here is going to equal 1 over sine x minus cos x I'm going to leave as cos x over 1. I try and change them as much as I can into coses and sines. So cotan, yes, I could do 1 over tan, but there's a better option. What can I make cotan be? Cos over cos x over sine x. And I always, if I have a fraction side by side, I'll put the cos x over 1 each time, because you do numerator times numerator, denominator times denominator, and it takes away people making oopsies. So here we're going to have 1 over sine x minus cos times cos is cos squared x over sine x. When you have common denominators, you can add or subtract when you have common denominators because you can write it all over the one denominator. So now I can go 1 minus cos squared x over sine x. And we just went over this. What is 1 minus cos squared x the same as? Let's go back up here. We see variation. 1, bring my cos squared x over. 1 minus cos squared x is the same as what? Sine squared x, right? So now I'll get sine squared x over sine x. And sine squared x is just sine x times sine x. So one of these can cancel, and this actually just equals sine x. Okay, that's how I simplify it. But I could ask you to do non-permissible values. Because there's a denominator here, isn't there? And the denominator is what's in it? Variables. What's in my denominator the whole way through? Sine x. So I would have to say where sine x can't equal 0. X can't equal, where does sine x equal 0 or y equal 0? 0, pi, 2 pi, 3. So it's just pi and e pi. Just keep practicing our non-permissible values.